Okay, so get this. Scientists are shooting light through, like, super-cooled atoms. And get this, sometimes it's like the light arrives before it left.
Yeah.
Yeah, you heard that right. Negative time is what some are calling it. And you've sent over a stack of articles and discussions about this. So,
It's definitely one of those things, in physics that makes you rethink what you thought you knew. We've got that Reddit thread
yeah.
from science, always good for some interesting takes. Plus, we've got excerpts from the actual scientific paper, some summaries, even a piece from The Independent.
Wow. Okay. So before we warp the very fabric of space-time, what did these scientists actually do to get these crazy results?
Okay, so imagine a cloud of rubidium atoms chilled to almost absolute zero, like crazy cold. Now, picture shining a pulse of light photons through this cloud. What the scientists were measuring was not just how long it took the light to pass through, but also how it interacted with those atoms along the way.
Interactions like making the atoms do a little dance as the light zipped past.
Sort of. So when a photon hits an atom, it can transfer some of its energy, causing the atom's electrons to briefly jump to a higher energy level. Think of it like the atom is catching the photon's energy and getting briefly excited.
Okay, I think I get that. So we've got excited atoms and photons whizzing through a cloud.
Yeah.
What's the moment, the thing that makes this so weird?
Right, the moment is that sometimes the photons exited the cloud faster than they should have,
What?
based on how much time they should have spent interacting with the atoms. It's as if some of those photons knew a shortcut, arriving at the finish line before they even finished the race.
Hold on. Faster than light. Doesn't that break, like, a fundamental rule of the universe?
That's where it gets really interesting. It's not about breaking the speed of light. It's about this mind-boggling concept called group delay in optics.
Group delay. Is this where things start to sound like a science fiction movie?
Maybe a little. Okay, imagine a group of photons all traveling together as a pulse of light. When this pulse passes through a material, it usually gets slowed down a bit, right? Group delay is simply a measure of how much that pulse is delayed.
Okay, that makes sense. Light slows down in different materials. It's why a straw looks bent in a glass of water.
Exactly. But here's the wild part. Group delay can actually be negative, meaning the peak of the pulse can emerge from the material earlier than you'd expect, even though nothing is actually traveling faster than light.
Okay, so how does this tie back to those excited atoms and this idea of negative time?
Well, the researchers found that sometimes the average time those rubidium atoms spent in that excited state was also negative.
Hmm.
It's as if the atom was somehow affected by the photon before the photon even finished passing through it. Imagine being tapped on the shoulder a split second after you felt someone walk past you. It messes with your sense of cause and effect.
Wow, yeah. So are we saying goodbye to our understanding of time as we know it? Can I book my trip back to the future now?
Not quite. As tempting as time travel sounds, that's not exactly what's going on here. It's not a violation of causality as we currently understand it.
Okay, my brain needs a minute to catch up. We've got photons potentially influencing atoms in the past, but it's not time travel. I need a little more explanation on this, especially how they actually measured these tiny time differences. Didn't you say something about a second beam of light?
Right. Measuring anything on the quantum level is tricky, but these scientists used an incredibly precise technique involving something called phase shifts. Instead of measuring time directly, they measured how the interaction with the atoms affected the light itself.
So shining a second beam of light through the atoms somehow gives us a way to measure time. You're going to have to break this down for me.
Okay, so imagine two beams of light passing through the atoms. We've got our main beam, the one potentially experiencing negative time, but we're also shining a second beam, call it the probe beam, through the atoms at the same time. This probe beam is tuned to a slightly different frequency, so it doesn't interact with the atoms in the same way as the main beam. Think of it like two ships passing in the night money. One is our time-bending ship, and the other is there to observe its wake.
Okay, two beams, one time bending, one observing. I'm with you so far. But how does observing a second beam tell us anything about time?
Okay, so this is where it gets really cool. You see, light travels in waves, and those waves have peaks and troughs, just like waves in the ocean. The relationship between those peaks and troughs is called their phase. Now, when the probe beam passes through the rubidium atoms, it interacts ever so slightly with those that have been excited by the main beam. This interaction causes the probe beam's phase to shift like its peaks and troughs get nudged slightly out of sync.
Okay, I'm vaguely remembering something about waves being in phase or out of phase from high school physics. Something to do with how they add up or cancel each other out.
You got it. When waves are in phase, their peaks line up and they combine to make a stronger wave. When they're out of phase, the peaks of one wave line up with the troughs of the other, and they can actually cancel each other out.
So by measuring how much the second beam's wave shifted, they could tell how much the first beam interacted with the atoms, even if that interaction seemingly happened in reverse.
Precisely. It's mind-boggling how they can measure these incredibly tiny phase shifts. We're talking about differences on the order of millionths of a degree. It's like measuring the width of a human hair from miles away.
That is some seriously impressive measurement.
Mm.
But how does measuring these tiny phase shifts actually translate to measuring time, let alone negative time?
Right, so remember what we were talking about with group delay? The amount a pulse of light is delayed, or in this case seemingly sped up, is directly related to how much its phase changes. So by meticulously measuring the phase shift of that probe beam, the scientists could work backward and figure out the group delay experienced by the main beam. Even when that delay was negative, it's like using a super sensitive stopwatch that measures time based on how much a light wave is shifted instead of how many seconds have ticked by.
So we're not actually watching the atoms interact with the photons in real time. We're looking at the after effects by analyzing that second beam of light.
That's a great way to put it. And this method is crucial in the quantum world because, as you may know, directly observing a quantum system can actually change the outcome.
It's like trying to catch a snowflake. The moment you try to look at it too closely, it melts away.
Exactly. This phase shift method allows us to indirectly observe and measure what's happening without disturbing those delicate quantum processes.
This is all incredibly clever, but I have to admit, I'm still struggling to wrap my head around what this negative time effect really means. It's like trying to imagine a new color you've never seen before.
It's understandable to feel that way. This experiment really challenges our everyday intuition. But before we dive deeper into the potential implications, we should probably address the fact that not everyone in the scientific community fully agrees with this negative time interpretation.
Oh, there are other explanations for what's going on. I have to admit, as fascinating as it is, the idea of negative time does seem, I don't know, maybe a little too wild to be true.
Science wouldn't be any fun if we didn't have some, healthy skepticism and debate. While the results of this experiment are incredibly intriguing, it's important to remember that we're dealing with statistical measurements based on observing the collective behavior of many photons and atoms. And whenever you're dealing with statistics, there's always room for alternative interpretations.
So what are some of the other explanations being put forward? Are there any, holes in this negative time theory?
One of the key things to remember is that this experiment relies heavily on what we call post-selection and weak measurements. Essentially, we're talking about techniques that allow us to extract information about quantum systems in a very clever, roundabout way without disturbing them directly. But because of the nature of these techniques, interpreting the results can be, well, a bit tricky.
So it's not as simple as just pointing a stopwatch at an atom and saying, negative time.
Not quite. We're looking at subtle patterns and correlations in the data, which, while compelling, don't necessarily prove that time itself is flowing backward. Some physicists argue that the term negative time might be a bit misleading, and that the observed effects could be due to other, more subtle, quantum phenomena.
Like what, for instance? Give me some of those alternative explanations.
One possibility is that what we're seeing is a manifestation of quantum entanglement, that spooky connection between particles that Einstein famously called spooky action at a distance.
Entanglement. So instead of the photons actually traveling backward in time, it's more like the atoms are secretly coordinating with each other through their quantum connections, creating the illusion of negative time.
Exactly. It's like the atoms are involved in some elaborate quantum dance, and the way they interact with each other makes it seem like time is flowing backward, even if it isn't. It's a fascinating alternative that demonstrates just how interconnected and counterintuitive the quantum world truly is.
Okay, now my head is really spinning. Entanglement, negative time, photons potentially influencing the past. It seems like the more we delve into the quantum world, the stranger it gets. But that's what makes it so fascinating, right?
Absolutely. It's like we're constantly peeling back layers of an infinitely complex onion, and with each layer, we uncover new mysteries and possibilities. But what's particularly intriguing about this experiment are the potential implications it could have on our understanding of information processing, particularly when it comes to the development of quantum computers.
Quantum computers. We can't have a conversation about mind-bending physics without them coming up.
Yeah.
But what's the connection between this negative time effect and building these super-fast computers of the future?
That's where it gets really exciting. One of the biggest hurdles in building powerful quantum computers is figuring out how to store and manipulate information in a way that takes advantage of, quantum weirdness, things like superposition and entanglement.
Right, because in the quantum world, things can be in multiple states at once, and particles can be linked across vast distances. It's like the universe's way of playing a cosmic game of chess where all the pieces can move at once.
A very apt analogy. And what's fascinating is that this experiment, whether we interpret it as negative time or something else entirely, hints at the possibility of manipulating these quantum states in ways we previously thought impossible. Imagine being able to store information in the state of an atom before it's even been excited by a photon.
It's like writing the answer on a chalkboard before knowing the question. That kind of mind-bending potential is what has everyone so excited about quantum computing, right?
Exactly. The ability to manipulate and access information in this way could revolutionize fields like medicine, materials science, artificial intelligence. The possibilities are truly staggering.
It sounds like this one experiment might have opened a door to a whole new way of thinking about information processing. And it all comes back to questioning our fundamental understanding of time.
And light,
Mhm.
and matter, and the very fabric of reality. But you're right, at the heart of this is the question of time. This research, along with other recent breakthroughs in quantum physics, is challenging us to reevaluate what we thought we knew about something so fundamental to our experience of the universe.
For me, one of the most intriguing aspects of all this is that it reminds us just how much we don't know. We've spent centuries building up our understanding of physics, and suddenly we're discovering that at the quantum level, the rule book might be completely different.
It's incredibly humbling, isn't it? It's a reminder that the universe is full of surprises, and our intuition, while useful in our everyday lives, can be a poor guide when we venture into the quantum realm.
It's like we've been playing checkers, and suddenly the universe has introduced us to a game with infinite dimensions and pieces that move backward in time. But even if we can't fully wrap our heads around it, just contemplating these possibilities is exhilarating.
Absolutely. And who knows what other counterintuitive, mind-boggling phenomena are still out there waiting to be discovered? What if this negative time effect is just the tip of the iceberg? A glimpse into a universe far stranger and more wondrous than we ever imagined.
It's a tantalizing thought, and one that I'm sure will fuel the imaginations of scientists and science fiction writers alike for years to come. But even if we set aside the more fantastical possibilities, the implications of this research for our understanding of the universe are profound.
Indeed, it speaks to the power of curiosity, the importance of challenging assumptions, and the sheer audacity of seeking answers to the universe's most perplexing puzzles.
Well said. This deep dive into the world of negative time has been an incredible journey. I feel like I've learned more about the universe in the past hour than I have in, my entire life. And while I still might not be able to fully grasp the concept of time flowing backward, I have a newfound appreciation for the elegance, strangeness, and sheer wonder of the quantum world.
And that's what it's all about. It's not just about finding answers, but about embracing the mystery and never losing that sense of awe and wonder.
Well, on that note, I think it's time for us to step back from the quantum realm, at least for now. But I have a feeling this is a conversation we'll be returning to as new discoveries inevitably come to light.
I have no doubt about that. Until then, keep questioning, keep exploring, and keep looking for those moments that make you question everything you thought you knew about the universe.
And to our listeners, thank you for joining us on this deep dive. Until next time, keep your minds open and your curiosity engaged.